In this chapter, we are looking at discrete random variables. As I kind of identified in the overview of this chapter, um, these are important types of variables to look at because you encounter them frequently when you're conducting an experiment. So for those of you who are psychology students, for instance, or even sociology students, you would see this a bit more often. So when we say something is random, what we're saying is that we have no certainty as to which outcome will occur. So like rolling a dice. Rolling a dice is a discrete random variable, the outcome of that. Because you know that it's going to be a 1 through a 6. You don't know which one of those 6 options it's going to be, but you do know that it's one of those 6. And rolling a dice produces an outcome that is discrete. Something is discrete if we basically know what all the possible outcomes are, which we do. They are 1 through 6. So it has basically a known, a finite number of values of possible outcomes that could come out. Okay, so let's. I don't know why it's getting like that. Okay. So as an overview of what we're looking at here, so we're starting by looking at understanding again what a random variable is, learning the difference between discrete and continuous, which I've kind of already done some of those things already, but we'll talk about them in more detail. Then what we want to do and what's important for us is understand the probability distribution of each of those possible outcomes, those discrete random variables. And then we're going to take what we learned previously about the mean, the variance, and the standard deviation, and we're going to learn how to compute those for these discrete random variables. And then we'll finish that up by looking at a random variable that is binomial. And then we'll kind of finish up here then seeing that a random variable is a type of binomial random variable. Okay, so the book chapter starts off with just a description of what's impossible. They call it experiments, but it makes me seem like it's someone in a lab coat and something like that. It doesn't have to be like that. It's really just something happening, and that outcome, the thing that happened, trying to understand how probable that thing is that happened. So these are 4 examples: rolling 2 fair dice. Oh, I see. So you're rolling 2 dice that I guess are not constructed in a way to make them unfair, and you're looking at the outcomes where you add up the sum of the 2 dice, and if you sum up the 2 dice, what you're looking at here are what are all the possible values. So in this case, right, you get 2 1s. That would be 2. You get a 2 and a 1, that'd be a 3, and so on and so forth. So those are discrete outcomes because we know all the possible values. But yet it's random. Because we're rolling 2 dice, and we really don't know what options are going to show up until they just show up. Yet, as this chapter is going to emphasize, we can calculate the probability of getting the 2 dice to sum up to 2. Which would simply be, in this case, the probability of getting a 1, and then the probability of the other die having a 1 as well. The second experience is flipping the coin repeatedly and trying to figure out how often would you have to flip it to get the coin to be a heads. So then you can just count 1, 2, 3, 4, and at some point you would get ahead. Now, in terms of the voltage at an electrical outlet, so here it's probably still going to be discrete, but certainly random. It's discrete in the sense here that we're saying that it's if it's a 120 volt outlet, it's probably going to be somewhere between 118 and 122. It's going to be some number between that set. And then the final one is how long does it take a light bulb to burn out? Which sounds like a bad joke. That would obviously be important if you're an engineer or that type of thing. Okay, I'm going to just pause for a second here. Okay. So, just to repeat what I've already kind of mentioned both in the overview and the beginning of this lecture. So the random variable, again, itself, is any number that's generated because you're conducting a random experiment. Random meaning that no outcome has any greater probability of occurring than another. So most of the time here, what we then do is we denote the variables themselves with capital letters and then the actual outcomes with lowercase letters for the values that those the capital letters can take. Again, it's discrete. A random variable is discrete if the outcomes, all the possible outcomes are known and things are finite. Otherwise, the random variable is going to be continuous. And that would be if you have an interval of numbers. So if we go back over here, right, here we've got intervals rather than discrete. Here we'd have 2 discrete, 2 continuous. Okay, so when we look, the most important thing we would then try to do, especially since this is a statistics course, is we'd want to look at the probability distribution for that entire random variable. And so what we would do is, since it's a discrete random variable, we're going to list all the possible outcomes, and then we're going to look at the probability that each of those values could happen over time. The probability itself would have to be between 0 and 1, 0 being can't at all happen, 1 being a certainty that it would happen. No matter what the probabilities are, as long as they're between 0 and 1, everything then has to add up to 1 across all the probabilities of all the values that could occur. So let's do an example here. If we toss a coin and we toss it twice, the capital letter, the random variable, in our case, we're going to say that it's the number of heads that you're going to get. So the options would be you could get 0, you get 1, or you get 2, right? You can get 0 because you toss it twice and you get tails both times. You get 1 because you toss it twice and one time you get tails, one time you get heads. Or you get 2, you toss it twice and each time you get heads. So with that said, probably what I said makes sense, saying it out loud like that. But what we want to do now is construct the probability distribution for that variable. And then we're going to want to find the probability that at least we'll get heads at least once. So, as I said, possible values are 0, 1, and 2. So all of the possible outcomes would be heads, 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 tails, tails, heads, tails, tails. Each of those 4 are equally likely, right? Because it's a random tossing of a coin. So each are equally likely, then you would see that it doesn't matter which order that things are coming in. So heads and tails and tails and heads, is essentially the same. So that's why it's a half. And then there's a 25% chance of getting both heads and a 25% of getting both, getting both heads would be this one, because that would be 2 heads, and then 2 tails. That would be getting 0 heads, because the x is, again, number of heads. And so there's our probability distribution. If we want to look at how many heads are flipped, you have 0, 1, or 2. With a 25% chance, because there's one outcome where there's, one, I keep doing that, one chance out of 4 that you get no heads. 1 head would be a 50% chance, because there's 2 outcomes out of the 4 where you get at least 1 head. Or you get only 1 head, you only get 1 head. Not at least, but 1. And then a 25% again that you get 2 heads right here. And so the way we write that out then is that greater than or equal to 1, because that would be our at least 1 head. So it'd be both probability with 1 and with 2. We add those up, because in this case they're mutually exclusive, which then gives us a 75% chance of getting at least 1 head, because that would be both 1 and 2. So 75% chance. So far, not too difficult, right? And then we could graph this out. And if we graphed it out, then what we would see is, if we graphed out the frequency distribution, what we would see is that 0 and 2 both have a 25% probability, and 1 has a 50% probability. So, if we want to now look at the mean of a discrete random variable, what we know is if our discrete random variable is our x, then the mean, it's found by taking the summation of the values times the probabilities. So what that essentially means here is that we can, if all of our possible outcomes are -2, 1, 2, and 3.5, and each of these 4 probabilities exist, then we essentially add up -2 times 0.21 plus the outcome of 1 times the 34% probability it has of happening, plus the outcome of 2 times its probability, plus the outcome of 3.5 times its probability. Sum those all up, and there's our mean. So that gives us a pretty good understanding of the center of that. But now once we've calculated the mean, we typically also want to know something about its variation. So let's look at the variance. The standard deviation, that would be how much variability we have between each of the trials of the experiment. What we would do is take each of the values and subtract the mean, square it, and multiply it by the probability. We could then distribute the squared, so then we could get the summation of the outcomes squared times the probability minus the square of the mean. And so we see an example of that right here. So let's take our first example that we already solved for. 4 possible outcomes, 4 different probabilities, those 4 different probabilities adding up to 1. We already solved for that mean of 1.135. If that's unfamiliar to you, we just solved that right here. Now, you can make your life easy, and you could do this second equation right here. But it is the same as doing it like this, and I actually prefer doing it this way as well. It just makes you just introduce one less chance that you could screw something up. By that I mean, right, if you try to simplify it and make it look like this, you run the risk, right, of I don't know, putting a wrong number somewhere. It's just easier to take the value minus the mean, square it, and then multiply it by the probability, because that's just a pretty consistent way of solving it. Okay. And so that's what you see here. So then I take each of the values, -2, 1, 2, and 3.5, and for each of those four, subtract the 1.135, take the square of each of that difference, and then multiply it by the probability, and add. So now I've solved for my mean already, and now I've solved for my standard deviation. Or, sorry, the variance, not the standard deviation. The standard deviation is going to be the square root of the variance squared. So we could take that 2.424 why are they saying, sorry, I'm thinking, calculate something here. I'm just checking their work here. Oh, sorry. No, they already did square it. Okay, never mind. Okay. So taking the square root gets us 1.85. And sorry, I'm just trying to make sure that their math was correct. Okay, 1 second here. Can't tell if they've made a typo or not. But they did not. Nope, it's all good. Okay. So if we look at this distribution from a binomial perspective, then what we're seeing is we could construct this, I guess, in a way where if a binomial distribution would occur if there are two outcomes. So that's the binomial part. Success or failure. That's kind of a classic binomial distribution, right? Or like if you're an electrician, right? Either you've got electricity or you don't have electricity. So the probability of each of those would be P, and the N would be the number of times that you get let's say a success or a failure, whatever your parameter is there. So you'd be looking at the probability of getting one of those two outcomes in the binomial distribution. So what that means for us here is that if we're looking again at a binomial random variable with parameters n and p, then we're going to take n factorial. So now what's n factorial? N factorial would be, in this case, most of the time it's like 1, if it's 2, if the n factorial is 2, it would be 1 times 2. If it was 3 factorial, it'd be 1 times 2 times 3. So factorial, n factorial, so whatever your number is, let's say it's 5, then it would be 5 times 4 times 3 times 2 times 1. So n factorial over x factorial, where x factorial would be your whatever your integer is, again multiplying it out. And then in parentheses here we've got, and then you would just take n minus x and take the factorial of that. Now, the nice thing about taking this class online, before you start getting like really weirded out here, you're going to have these equations available to you. You know, you can look them up. I'm going to try to give you enough time on the exam to look them up. I'm not expecting you to remember them. The exam is going to be in La Lima, so you will have your Flat World book and all these slides and everything available to you to do it. So don't get too freaked out at this moment. Just trying to understand the process we're going through to solve this. We're going to take that ratio of n factorial over x factorial n minus x factorial times p to the x times q to the n minus x. So all you're really doing here, and what's kind of makes this a little bit easier, is all you're then doing is just plugging in the needed numbers. Okay, so then we have an example here. We have financial fraud, where 17% of the victims of financial fraud know the perpetrator, the causer of the fraud, personally. And we're asked to use the formula, construct a probability distribution for this case. And then find the average number of cases a day and how many cases a day occur most frequently. Okay. I'm going to pause the video here, if only because, as some of you can see, I have a meeting here that just starts at 1. So I'm going to pause the video here while I do this needed meeting. Okay, picking up on this. So again, what we have here is a binomial distribution. Either someone is a victim of financial fraud or not. And then what we want to know is that we know that 17% of these victims of financial fraud know their perpetrator, know the person who defrauded them personally. So if I had 5 individuals who had financial fraud, did they, I want to know the probability that they knew that perpetrator personally. The investigator here is going to look at 5 cases every day. How often each day, what's the most frequent number of times they're going to find that the fraud victim knew the causer of the fraud. And then how many on average. So that's what we're going to solve here. So let's look at this. Okay. So n is 5. N is 5 because they're looking at 5 a day. And we already know from the larger sample is that the probability is 17% of the total number would know the victim of the fraud would know the causer of the fraud personally. And so then how many do not know the causer of the fraud personally? Well, that would be 1 minus that probability. So 83% do not know the person. If the investigator is looking at 5 cases a day, then the number that they would find where the person knows the bad person, let's just start calling it the bad person, the person causing the fraud, they either find 0 people know that bad person, 1 person knows the bad person, 2, 3, 4, and 5. And so then what we need to do is solve for each of those probabilities. And we do that with this equation. So going back over here. So we would then start to solve this. And I know, again, I'm well aware that it really looks intimidating. But what I'm trying to impart here, encourage you to believe me that it's really just plugging in the numbers and then throwing it in the calculator. And that's really all that on some level statistics is. It's just throwing stuff into the calculator and having it do it. So in this case, 5 factorial over 0 factorial, 0 people knowing the bad person, times 5 factorial, times the probability with the outcome, times the 1 minus that probability, times the outcome. Which, if you plug it into your calculator correctly, gets you 0.3939 repeating. And then you would just repeat that for 1, 2, 3, 4, and 5. Okay. Where the n is going to change and the n is going to change. I'm sorry, the n is going to change. The n's not going to change. The n is going to be the 5 is going to be 5. So it's always at 5. My apologies. What's changing is our x, the integer that we're actually having here. So this would be 5. So the next one would be, let's write this out here and hope that the pen doesn't explode in size here. So that would be 5 factorial over 1 factorial times 4 factorial times 0.17 first, 0.83 to the 4th. And let's confirm that that is true. So 5 factorial, just so we can kind of see this here, 5 factorial is equal to 120. How did I get that? In my calculator, I typed in 5 times 4 times 3 times 2 times 1. So I would have 120 over 1 factorial is just 1 times 4 factorial. That would be 4 times 3 times 2 times 1. Should be 24 times 0.17 times 0.83 to the 4th power. That's 0.47. I'm just rounding to 2 significant digits. So it'd be 120 divided by 24. That's 5. So this is equal to 5. So 5 times 0.17 times 0.47 is equal to it's probably just caused. Okay, well, I shouldn't have rounded so sloppily. But, okay. So I rounded a little bit sloppily here, and I think that caused some problems. Let's try to fix this here, make sure I'm accurate here. 120 divided by 24 is 5 times 0.17 times 0.83 to the 4th power. Yeah. I can't show it to you, but sorry. In your calculator, if you want to get the exact same number as this, don't put in just 0.47. Put in 0.83 to the 4th. So in my calculator, what I typed in was 5 times parentheses 0.17 times parentheses 0.83. And then if you're looking at your calculator, you should have that little hat symbol. So type in that little hat symbol, 4th. And then I got 0.40339.5, which is what they got there. So I just repeat that process for 2, 3, 4, and 5. So now to answer so now we know what the probability is of each of these. That a person would find 0 cases, 1 case, 2 case, 3 case, 4 case, 5 cases. And so then we have to know which one is most likely. So then we just have to find the probability that is the highest. In this one is the highest probability. So to answer our second question, find the most frequent number of cases each day. That would be the one with the highest probability. So that would be the 1 case here. And then for the average number of cases, finding the mean. Again, we're just plugging and chugging. And that's all we're doing here. So we're going to take each of the outcomes, 0, 1, 2, 3, 4, 5, multiply it by its probability of occurring, and then add those up. And that gets us our mean. Okay. This is not different people who teach the stats course take on different methodologies. I am not one to require you to memorize equations. It's not important to me. I don't memorize the equations myself, so why should I ask you to do it? Star this, make a note that these are the equations that we have here for finding our mean, our variance, and our standard deviation. But there's not much more I would do beyond that. Except on the next slide where you do have to solve for some of those. But again, all you're doing here is plugging in the numbers and solving for it, for mean, for variance, and for standard deviation. Sorry, I'm just making sure I've got... One second. Sorry. I'm just making sure I haven't forgotten anything. Yeah, I don't... I thought this was a good book. There is an error here. I can't deny that there is an error here. And I kept second guessing myself. This should be 2.424. Which would then make that different as well. 1.55. I don't know why they put 3.424 because we had solved it 2 slides previous to that as 2.424. Unless someone's seeing something that I'm not. I believe that at least the slides have an error here because we solved it as 2.424. Unless I'm missing something, which is always possible. Okay, so this was just plugging in those numbers and solving for it. Okay. Okay, I'm just going to pause here. Okay, so I'll stop all these text always coming off. Okay, so if you look in the textbook, I'm looking on page 124 if you're looking at the physical book. They're just making a note here for you that the binomial probabilities table is cumulative. In terms of most good textbooks have a sorry, I'm just looking here. If you look on the appendix or chapter 12 in the textbook, there you would see the cumulative binomial probabilities. So go to chapter 12 of the book and you should be able to see that. I wouldn't worry too much about getting too confused about that because the graph on page 125 should make it a little bit more apparent. Let's talk about how you actually would use the cumulative probability distribution. So a student takes a 10-question true-false exam. Find the probability that the student gets 6 questions right by simply guessing. So that would be two possibilities, true or false, that they're going to get 6 right, and then find the probability that they're going to get a grade of 60% or better. So the first one is exactly 6. The second one is greater than or equal to 60%. Okay. So with that, let's start to solve it. So in this case, I'm also looking at the chart here too, just to ensure that everything is accurate here. Oh, I see what they did. Okay, never mind. Okay. So, probability of getting at least 6 correct, of exactly 6 correct would be, again, falling back to our earlier equation, 10 factorial over n minus x, which would be 6, because that would be 10, let's write this down here, just so we don't get too confused here quickly. That n is equal to 10, x is equal to 6. So we have n factorial over x factorial, n minus x factorial. Then the probability of, it's either true or false, that's why it's 50% probability, to the x, and then the 50% probability which is found by taking 100% minus 50%. So that's 50% to r n minus x, which is 4. And solved. Then, if we need to get at least 6 correct, so that would mean 6 or greater, well then it changes things a little bit. So that would mean that we need to take the probability for 6, 7, 8, 9, and 10. In terms of looking at the binomial table, I just want to make sure here. Sorry, be patient with me for a second. Sorry, I need the left tail. Sorry, I'm just looking at our appendix here. Oh, I'm sorry, 5. Okay. Okay, so since the probability, the cumulative binomial probability in appendix for chapter 12, it's the left side. So instead of finding 6 or greater, we're not finding that probability. Instead, we need to find the inverse, which would be 5. So what we need to do there is we need to find the probability for less than or equal to 5. So for less than or equal to 5 is 0.62, so that's correct. Giving us then our value, so we would take 1 minus that probability times 5. Giving us a result of 0.37. So here's another way to look at this here. Okay, so binomial I mean, you can use the one from the book, which is fine. Hey, look, someone from the math department here for us solved it too. Okay, so what we can see here, right, is that for n, right, we have a sample size of n, 10. And then for 5, 4, 3, 2, 1, with a probability of 50% because it's true or false. So we would go down the 50% column here to 5, and that's where we see this 0.623. To be honest, I think this is a little bit easier to use than the book. So that's where we got the 0.623 from. Again, n is 10, because you're taking 10, there's 10 questions. You're finding what are the chances of getting 5 or less, where the probability of each outcome is 50%. So that's why we have 6.623. That's where we go right there. Okay. And then these are just our reminders of the key terms. Something I think will help with each of these chapters is I'm going to walk you through how to do the homework, and then it will give you at least a little bit less of a theoretical understanding of the material and a little bit more of the practical hands-on part of it. Okay, so that'll at least end the formal lecture here, and then I'll start talking about the homework assignments.